Today we will be covering 10.3 and 10.4 in the textbook, which includes polar coordinates and curves in relation to calculus topic.
The first question asks you to sketch the graph and find the area outside r equals 5 plus 6 sine theta and inside r equals 2. The first step is to figure out what type of graph r equals 5 plus 6 sine theta gives you. And because that equation is in the form a plus or minus b sine theta, you know that the equation is going to give you a limicon. And because a is less than b, because 5 is less than 6, you know that the limicon will have an inner loop.
We know that the second equation, r equals 2, is a circle because the radius is consistently 2 all around the graph. Now we need to plot the coordinates for the polar equations. So for r equals 5 plus 6 sine theta, we created a table. And the way we created this table was we substituted the angle theta into the equation and got a value for r. So for example, for the angle of 0, it's at that angle, and you count out 5, and we plot that point. And then we go all the way around to get the graph. Now we need a graph r equals 2. So like we said, it's just a circle, so just graph a circle with a radius of 2 centered at the origin. The area that is outside of 5 plus 6 sine theta and inside of r equals 2 is the area that we are shading in right now.
In order to find the shaded area, we must find the points of intersection by setting the two equations equal to each other, because the shaded area is enclosed by these points.
By setting the two equations equal to each other, we get that sine theta equals negative 1/2. So we know that theta equals 7 pi over 6, 11 pi over 6, etc. And so if you look at the graph, we know that that point is 7 pi over 6 because it is the first point at which the two graphs intersect. And that is 11 pi over 6. The formula to find the area of a polar graph is a equals 1/2 from a to b of r squared d theta. We zoom into the graph and plot the line that represents 7 pi over 6. So from 7 pi over 6 to the point where the limicon touches 0 is this area in pink. And from 7 pi over 6 to 3 pi over 2, it's this area inside of the circle in blue. If we want to find the area that's outside the limicon but inside the circle, we need to find the purple area, which is the blue area minus the pink area. The area that is shown here is only half of the total area that we want to find, because the limicon and the circle are symmetrical across the y-axis. So all of the equations that we will be showing is 2 times 1/2.
To find the blue area, simply plug in the r, which is 2, into the area equation. That gives you half times the integral from 7 pi 6 to 3 pi halves of 2 squared d theta. We multiply this by 2 in order to get the total area of the blue area. To find the pink area, the equation is half times the integral from 7 pi 6 to some theta of 5 plus 6 sine theta squared. That unknown theta, where the limicon point crosses the origin, is simply when 5 plus 6 sine theta equals 0. Solve for theta, and you get theta equals sine inverse of negative 5 over 6. So, the final equation for the pink area looks like this.
The final equation for the total area that we want to find looks like this. So it equals the integral from 7 pi over 6 to 3 pi over 2 of 4 d theta, which is the blue area, minus the integral of 7 pi over 6 to sine inverse of negative 5 over 6 of 5 plus 6 sine theta squared, which is the pink area d theta. So this will give you the purple area.
This expression isn't solvable by hand, so just plug in the integrals into the calculator. The blue area gives you 4 pi thirds, and the pink area is about negative 296.005, but you can store the exact value in the calculator. 4 pi thirds minus negative 296.005 gives you an estimated value of 273.194, so this is your final answer.
A common mistake for this problem is drawing the graph too small and not noticing that when you plot the line for 7 pi over 6, it actually goes into the limicon as well. And so as you can see here, this smaller graph that we made, you can't really notice. So instead, some students may just find this area and be done, when it's actually supposed to minus this as well. The second question asks for us to set up the integral to find the arc length of one petal of the polar graph r equals 4 sine 5 theta. First, let's graph it. It is not necessary to be accurate for this problem. Equations in the form a sine b theta are rose curves. The a value, or 4, is the length of the petals, and the b value, or 5, determines the number of petals. Because 5 is an odd number, we know that the rose has 5 petals. The graph should look something like this. Because sine is an odd graph, the first petal does not start on the polar axis. So it should be somewhere in the lower part of the first quadrant. Sine of pi over 2 is 1, not 0, thus the second petal is 4 on the angle pi over 2 and perpendicular to the polar axis. The other 3 petals can be found by either plotting points or just understanding that the graph is symmetrical and has 5 petals. The equation for arc length for polar equations is L equals the integral from a to b of the square root of r squared plus the derivative of r squared. So as you can see, the petal goes from 0 all the way around to where the curve touches 0 again. So in order to find where the curve touches 0 again, we need to set 4 sine 5 theta equal to 0. And you get theta equals pi over 5. Next, the derivative of r is 20 cosine 5 theta by the chain rule. Then plug in necessary values into the equation and you get this final answer. Because the question says to just set up the integral, we can stop here. Upon further simplification, we realize the equation needs a calculator to solve. The final answer is 8.40402. A couple of common mistakes with this problem is that students may forget that it's asking you to find the arc length of only one petal. So they'll set the interval instead of to pi over 5 just from 0 to 2 pi, and they'll find the arc length of the entire curve.
The third question asks for the horizontal and vertical tangents of r equals 1 plus cosine theta. Recall that an expression has vertical tangents when the denominator equals 0 and horizontal tangents when the numerator equals 0. So to find the tangent line, we need to find dy dx. The vertical tangent lines are when dx equals 0 and the horizontal tangent lines are when dy equals 0. So first, let's find dy. We know y equals r sine theta, so using the product rule we get dy equals r prime sine theta plus r cosine theta. As you can see, r is 1 plus cosine theta and r prime is negative sine theta, and plugging those into the equation we get this. You can pause the video to see all the steps for simplifying the equation, but eventually we get 2 cosine theta minus 1 times cosine theta plus 1. We set that equal to 0, solve for theta, and the values we get are pi thirds, 5 pi thirds, and pi. Now we need to find the points where the tangent line is vertical, or dx d theta is 0. Again, we go through the same process, find that dx is r prime cosine theta minus r sine theta, and plug in r and r prime into that equation to get dx d theta is equal to negative sine theta times cosine theta minus 1 plus cosine theta times sine theta. Again, you simplify to get sine theta equals 0 and cosine theta equals negative half, and the theta values are 0, pi, 2 pi third, and 4 pi third. A common mistake students make is forgetting that theta equals pi is a solution when finding both dy d theta equals 0 and dx d theta equals 0. And so they leave the answer showing that the tangent line is both horizontal and vertical at that point, which doesn't make sense. What you actually have to do in this situation is find the limit as theta approaches pi of dy d theta over dx d theta. If the limit of the slope is 0 as theta approaches pi, then you know that the tangent line is horizontal at that point because the slope is approaching 0. On the other hand, if the limit of the slope is undefined, then you know that the tangent line is vertical. So let's find out which type of tangent line pi equals theta gives us. Since we already found dy d theta and dx d theta, we can just plug those in and we get dy d theta is negative 3 times 0, which is just 0, and dx d theta is 0 times negative 1, which is also 0. 0 over 0 is indeterminate, so now we have to use L'Hopital's. This is the derivative of dy d theta, and this is the derivative of dx d theta, and what you get when you plug in theta equals pi is 0 over negative 1, which is simply 0. So at theta equals pi, the tangent line is horizontal. Using all the information we've gathered up to this point, we can finally answer the question and find all the coordinates. When the tangent line is horizontal, or dy d theta is 0, theta is pi thirds, 5 pi thirds, and pi. Plug those values into the original equation to get r, and the coordinates you get are 3 halves comma pi thirds, 3 halves comma 5 pi thirds, and 0 comma pi. So those are the points where the tangent line is horizontal. When the tangent line is vertical, theta is 0, 2 pi thirds, and 4 pi thirds. Plug those into r equals 1 plus cosine theta, and you get the coordinates 2 comma 0, half comma 2 pi thirds, and half comma 4 pi thirds. And that's how you solve the problem.
The fourth question asks us to find the slope of the tangent line to the polar curve at the given value of theta. So we're given r equals 2 plus 4 sine of 2 theta, and theta equals pi over 3. So it's not necessary to graph this problem, however it would be helpful to visualize approximately how much the slope is and to check your answer. So a helpful tip is that on a non-calculator portion of the test, not graphing problems like these would be the more time-efficient choice. So finding the slope in parametric, polar, or vector equations should be done using the equation for dy over dx. So for polar equations, the equation for dy over dx is r prime sine theta plus r cosine theta all over r prime cosine theta minus r sine theta. So the derivative of r, or r prime, is 8 cosine of 2 theta by the chain rule. So you plug in the r that you are given and the dr over d theta that you found into the equation. And when you simplify, you get 8 cosine of 2 theta sine theta plus 2 cosine theta plus 4 sine 2 theta cosine theta all over 8 cosine 2 theta cosine theta minus 2 sine theta minus 4 sine 2 theta sine theta. And then finally, to find the slope of the tangent line at pi over 3, just plug in pi over 3 into that simplified equation. So when you plug it in and then you simplify, and then finally you end up with 1 minus square root of 3 all over negative 5 minus square root of 3. And that answer is approximately 0.1087. And when you graph it, see at around pi over 3, right here, it seems to be right that it has the slope of a decimal. The biggest common mistake for this problem would just be either forgetting the equation for dy over dx or having a problem in the simplification. So a way you can avoid this is if you ever forget the equation, you can always just find dy over d theta and dx over d theta of the r equation, and then just plugging that into the top and to the bottom, and you find that when you simplify that out, it'll equal this equation in the end, because that's how this equation was derived. And then for the simplification errors, just double check your work if you have time at the end of the test.